force diagrams, you see how the forces are being applied, and then you apply F equals ma to that case, and you solve the problem. So Newtonian mechanics is essentially done in terms of forces and force diagrams. Force is applied, see how it is applied, and you solve the equation F equals ma. Now, Lagrangian mechanics is not done in terms of forces. That's the one main difference. It's done in terms of energies. There is energy of motion. That if some object is in motion, so it has energy. Okay? This is called kinetic energy. Now, there is also the energy of configuration. That if you have this plate right here and this cup is put here, so what I can do is that I can associate with this one certain energy, that if the cup is put here on the plate, it has a different energy, here on the plate it has a different energy. So regarding the arrangement of the system, there is energy of this configuration. This is the potential energy. Now you subtract the two, the kinetic energy and potential energy. Okay, this term that you get, it's called the Lagrangian. And what Lagrangian mechanics is about, that you use this Lagrangian, which is a kind of like difference in energies, right? Use this Lagrangian to solve problems. Well, how do you do it? What you do is, you, for any system, instead of now writing forces and force diagrams, you do the Lagrangian this way. You find how fast it is moving, write its kinetic energy according to how fast. You see that where in space it is present, how it is interacting with other things. Write potential energy according to that. Subtract them, you found the Lagrangian. Then there is, instead of F equals ma, you put it in the Euler-Lagrange equation. That is the fundamental equation of Lagrangian mechanics. You put it in Euler-Lagrange equation, and it's a differential equation. So you solve this differential equation, you can find your whatever variables you want to find, and that is how you solve the problem. One essential difference, F equals ma, and this one I told you that is in terms of forces, this energies. Another important difference, that here we can change our coordinates. That is, F equals ma is done, that this is one direction, this is one direction, and this is one direction. Okay, so there are three independent directions, and you write along these three independent directions only you are able to do your calculations. Now you might make a change of these directions, you might use angles instead, but that it gets really complicated, because when you use F equals ma, by changing these three directions into angles or anything, then the equations themselves change. That is what happens. The equation F equals ma will itself change. So normally you do everything in three directions. Okay, but if you want, you have a circle. In a circle, it is easier to not work with these three directions, but it is easier to work with angles. So what you want to do, you want to use F equals ma. When you use it, the form of equation will change. So gets complicated. But Lagrangian equations, like if you change from one coordinate, like these three directions, to other coordinates, so in terms of angles or in any other coordinates, the form of equation remains same. So you can change, use whatever coordinate just you want to, and you can use it still as good as any other set of coordinates. And this is really, you see, a powerful approach when it comes to quantum mechanics, because the same method can be extended as in quantum mechanics as Feynman's path integral formulation, right? So I told you there is also other, that is Hamiltonian mechanics, that deals with, instead of Lagrangian, that deals with Hamiltonian. This is also an energy based approach. So what it does is that I told you kinetic energy and potential energy, right? But you don't subtract them this time. This time you add them. Kinetic energy plus potential energy. This is the Hamiltonian. So, and then you use Hamilton